In section 5.4.2, we will learn how to solve exponential equations with unlike bases. So if we cannot get like bases and therefore set the exponents equal, what are we going to do? Well, we're going to use inverse functions to solve. Now, before we jump into this, let me bring to mind a very simple principle that you use every time you solve an equation. Let's look at this really simple equation, x plus 1 equals 4. Now, how do we solve that equation? You probably understand very easily that we subtract 1 from both sides, right? Now, why do we subtract 1 from both sides? How do you know that? Well, in order to solve for x, I have to apply the inverse operation of the operation that's applied, right? The operation applied to x here is plus, so I'm applying the inverse operation to both sides in order to undo that operation and therefore isolate x. Another example, let's look at 2x equals 10. A super simple equation. I'm confident you can solve this one. How do we solve that equation? Well, you know, we divide both sides by 2. The question is, that's so second nature by now that you don't even really have to think about it. But why do we divide by 2 as opposed to subtracting 2, adding 2? We divide by 2 because we're applying the inverse operation of the operation that's applied to x. Since x is multiplied by 2, we undo that operation with the inverse function. So when you solve equations, you are using the principle of inverse functions or inverse operations to solve equations. That's the principle that we're going to use to solve exponential equations with unlike bases. Now, here's a pop quiz for you. What is the inverse of an exponential function? What is the inverse of an exponential function? Hopefully you have been able to absorb, as we've studied Unit 5, that a logarithmic function and an exponential function are inverses. Exponential functions and logarithmic functions are inverses. So in the same way that we were able to undo the addition here with the inverse operation subtraction, or undo the multiplication here with division, we're going to undo an exponential operation with a logarithmic operation. Keep that in mind as we go through the algorithm. Another thing I want you to remember, whenever we have an exponential expression, we have a coordinating logarithmic form. If we have y equals a to the x, we can rewrite this in exponential form as log base a of y equals x. We practiced that a lot when we looked at the introduction to logarithmic function. That is the fundamental key for solving exponential equations with unlike bases. Okay, enough background information. Let's get going with our algorithm here. To solve an exponential equation, if I cannot get like bases, number 1, if necessary, isolate the exponential expression. Want to get it by itself. Then number 2, convert to logarithmic form. Okay, so we're going to take an exponential and we're going to convert it to logarithmic form. So what I'm doing here is applying an inverse, and that's going to help me solve the equation. Number 3, if necessary, sometimes your equation's solved at that point, sometimes you have a couple more steps. Number 3, solve the resulting equation. And we're going to have to add a step 4 here, right? What's step 4? Step 4, last step, should always be, check. Okay, so don't forget, once you solve the equation, check by substitution using your calculator. So here we go. Example 2, use logarithms to solve the following equations exactly. So we are dealing with exponential equations. Our unknown is in the exponent. And notice for the equation 5 to the x equals 11, there is not a common base. I cannot write both 5 and 11 as a power of a common base. So the algorithm or the method that we learned in 5.4.1, getting like bases, that's out the window. So here we're going to apply the inverse of an exponential operation, which is a logarithmic equation. And we're simply going to do this by converting to logarithmic form. So we're going to rewrite this as log base 5 of something equals something. Can you figure out where all the parts go? The 11 goes here, and the x goes here. So congratulations, you have just isolated x, and you have solved that exponential equation. Now that may not feel very satisfying to you because it's kind of a strange looking solution. What in the world does x equal log base 5 of 11 really mean? Well, what we're dealing with here is what's called the exact solution. So in the same way that pi is exact and 3.14 is approximate, we can approximate our solution to kind of get a better idea of what actual value is represented there. Now, I'm going to teach you something new on your calculator. You may already know this. If you don't, it's going to be good news. We can evaluate this logarithm with our calculator. So we're going to approximate log base 5 of 11. So if you'll press your math button, use your down arrow key, you got to go pretty far down the list. We're looking for an option called log base. It is, again, down on the list under your math menu, option A, log base. If I choose log base, then I can type in log base 5 of 11. Remember, the keys log log, that represents base 10. The key ln, that represents base e. So here we can evaluate a log with any base using that option. Notice here we can approximate this value. If we go to the nearest hundredth, this is about 1.49. So the approximate solution, and I'm going to indicate approximate with the squiggly equals, is about 1.49. This is the approximate solution. So if I use the approximate solution to check the equation, then I'm going to get an approximate equality. So 5 to the 1.49 gives me approximately 11. Now, I could also type in the exact value, 5, and then my exponent key. Now, I'm going to go to the math menu. This time, I'm going to arrow up from the bottom of the list because you can get there a little bit faster. And I'm going to choose log base, and we'll type in log base 5 of 11. Now, remember, that number represents the exact value, the non-terminating, non-repeating decimal expressed symbolically there. And we get an exact balance. So an approximate answer gives me an approximate balance to the equation. An exact answer gives me an exact balance to the equation. But at least now I know the solution is somewhere around 1.49. Let's try that again. 3 to the x plus 1 equals 7. Well, the exponential part is already isolated, so we need to go ahead and convert to logarithmic form. So we're going to rewrite this as log base 3. We go to the other side to get the argument, and the exponent pops out when we find a logarithm. Now, x is not solved for completely, so I do need to subtract 1 from both sides. When I subtract 1 from the logarithm, those are not like terms, so they cannot be condensed or combined. This is our exact solution. Let's go ahead and approximate this with our calculator, so at least we'll have a better idea of what value that number actually represents. So one more shortcut. If we go to the math menu, we've talked about arrowing down to the bottom of the list here to find log base, or if you go up, you can get there a little bit faster. Another way to get directly there is, remember, let me arrow up. That was option A. Okay, so whenever I press my math key, I can also do alpha A and that immediately picks up log base. Okay, that'll save you a few seconds, right? So log base 3 of 7 minus 1, we can approximate this, and I'm just going to go to the nearest 2 decimal places, 0.77. So x is approximately equal to 0.77. Again, this is the approximate solution. Okay, let's go ahead and check that, and I'm just going to use the approximation simply for the reason that it's easier to type in. 3 to the 0.77 plus 1, we should expect it to be in the ballpark of 7, and it looks like we've done a good job. Okay, let's try the next one. Observe this is an exponential equation because the variable's in the exponent position. We are unable to get like bases between 6 and 13. Therefore, we will convert to logarithmic form. As I convert this to logarithmic form, keep in mind I'm applying an inverse function. So in the same way that addition cancels subtraction, my logarithm here basically rearranges my exponential equation. It brings that exponent down where I can actually solve for x. Okay, let's add 5 to both sides. Log base 6 of 13 plus 5 is 3x. And then we're going to divide both sides by 3. By the way, I mentioned before, you can have parentheses around your argument or you can leave them off. Another reason that I prefer keeping parentheses around the argument is because I cannot combine these two numbers. The parentheses there kind of indicate 13's in jail. He can't come out and communicate with 5, right? He has to stay put. So the parentheses just kind of help your logic there. So I'm going to divide both sides by 3, the entire left side by 3. So my exact solution looks a little bit complicated. Log base 6 of 13 plus 5, all divided by 3. That is my exact solution. Exact in the fact that the way we have it written symbolically represents all the decimals associated with that irrational number. Let's go ahead and approximate this with our calculator. I do want to point out we have an operation going on in that numerator, so we need to enclose it in a set of parentheses. So I'm going to do the shortcut, math, alpha A, log base 6 of 13. Make sure you get out of your parentheses before you add 5. Close parentheses for your numerator and divide by 3. So this is about 2.14. So my approximate value, I could say x is approximately 2.14. Again, that is an approximate or rounded solution. Okay? One last problem. If you want to pause me and give it a try and then check back, that is a great idea. Okay. To solve this one, our exponential part is isolated, so I need to go ahead and convert to logarithmic form. Now, this one is reversed of what we're kind of used to, so I got to really think about the parts here. The base of the logarithm is the base of my exponential expression. 2 is the result of that exponential evaluation, and remember, the exponent is always isolated when we find a logarithm. To solve for x now, we just need to divide both sides by 3. And so our exact solution is log base 11 of 2 divided by 3. So when the instructions say solve exactly, we're looking for the symbolic form of the solution. Let's go ahead and use our calculator to approximate. We can do our shortcut, math, alpha A, log base 11 of 2. I'm going to get out of my parentheses and divide by 3. We end up with approximately 0.09. We need to round it up if we're going 2 decimal places, so how about 0.10? So x is approximately, remember the squiggly equals just indicate approximate as opposed to exact. If we want to check it, I'm just going to use the approximation. 11 to the exponent, 3 times 0.1 should be in the ballpark of 2 and looks pretty good to me. So now you have 2 methods for solving an exponential equation. Get like bases. If that's possible, it's a quick, easy, fast, efficient method. If you are unable to get like bases, then we convert to logarithmic form and solve the resulting equation.